we talked about how you can use a graph form and do y equals mx plus b, which is what you'll be doing in lab. You'll be graphing ln k on the y-axis, 1 over temperature in kelvins on the x-axis, and then you can use the slope right there to calculate your activation energy. So that's what you're doing in lab, okay? This is in lab, if you want to do a graph, minimum 3 data points, which is why in lab you have 3 data points. Okay, at least 3 data points to make a graph, and then you get a slope, and based on the slope you get from the Excel, you know that basically it says here negative the r, negative r times the slope is the activation energy. So that's how you'll calculate your activation energy in lab. Now, if you don't have 3 data points, you only have 2 data points. Okay, we will be using this equation right here. So don't use this in the lab because we will be using the graphical form. So in the lecture, we'll be focusing on the 2-point form calculation. This equation here is on your periodic table. Okay, it is on your periodic table. Your job is to know how to plug it in, how to solve it algebraically. So I want to show you maybe 2 examples here, how we can do that. Just remember, because the R here is like 8.314, 8.315 joules, moles Kelvin, your units needs to be matching that unit. So your activation energy needs to be in joules. Your temperature needs to be in Kelvin. It's very important because on purpose, the questions will give you units that are not that, and you'll have to remember to convert them over, okay? If you don't convert them over, then everything will it will be wrong because the units are wrong, okay? So let's go ahead and try an example here for that kind of problem. We'll do a couple of those and then we'll move on to the next part about reaction mechanisms. So let's see. Here's the question. Write the equation out. Zoom out a little bit. O2 plus CO goes to NO plus CO2. All right, so that's our equation, and it says the rate constant at 701 Kelvin is 2.57 molarity minus 1, S minus 1, and the rate constant at 895 Kelvin is 567 M minus 1, S minus 1. Find the activation energy. And units of kilojoules per mole, okay? All right, so go ahead and write out that equation for you guys. It is ln K2 over K1 equals EA over R, 1 over T1 minus 1 over T2. Notice how the 2 and 1 are flipped around here. So there are different forms of this equation floating around on the internet. So please don't mix them up, okay? Stick to the one you see on your periodic table. So it's this one that we're using in class, okay? Now, when you calculate your activation energy, it's gonna come out in joules per moles, but then later on convert it to kilojoules per mole, okay? It was nice, they gave us the temperature in Kelvin, which is good because a lot of times they will give you the temperature in Celsius. Never plug in Celsius here, okay? Always use Kelvin. All right, so and then this is the rate constant for this temperature, that's the rate constant for this temperature. So these are the rate constants here, these are the temperatures here. All you do is plug them in, and then we have R, right? And then you solve for your EA. All right. So I am going to be using 8.314 joules per mole Kelvin. Here you got to use the joule unit. So over here you have, let's go ahead and label this as temperature 1. This is rate constant 1. And we'll label the second one as temperature 2, rate constant 2. So you know, like, to not mix them up. Okay, so let's go ahead and fill it in. LNK2, which is that one, over K1, 2.57, equals the EA, which we're looking for, over R. We'll go ahead and put that in, 8.314 joules per moles Kelvin. I think on your periodic table it says 8.315, but you'll be okay either way, it's close enough. And then we'll do 1 over temperature 1, which is 701, minus 1 over temperature 2. All right, so then we work out the math and solve for EA. Okay, so this one's a little easier because you're asking for activation energy. The next one we'll do, sometimes they'll ask you for the temperature, sometimes they'll ask you for the K. So I'll work one where they ask you for the K, we'll solve for the K version, okay? So you just basically use this equation, use algebra to solve for different parts of the equation. So this part we're doing for EA here. So go ahead and put 567 over 2.57, get that number and take natural log of that, okay? And you end up getting something about 5.4 here. And then you can go ahead and put this in the calculator, 1 over 701, see what the answer is, put a bracket, and then minus bracket 1 over 895. So you need to know how to do these steps here. So for here, you should get something like 3.09 times 10 to the minus 4. Okay, and I'm gonna go ahead and write that out again. So a lot of students are having, I'm seeing so many in your lab that you are not doing your calculator correct, not putting the numbers in your calculators correctly and getting the wrong answer. Kind of like if you had to do, the most common mistake I was seeing is like, if you had to do your KF calculation, it's like the delta TF divided by I and M. And then instead of putting a bracket around I and M, you guys don't use a parentheses. The calculator does a different operation. So you come up with the wrong answer. So you need to know how to use your calculator. It's really important, okay? A lot of people getting their answers wrong. They didn't check it with me, so they're just gonna get points taken off because they did it wrong. So make sure you guys have your work checked. If you do it early enough, you'll have time to get it checked and get it fixed. Okay, so 5.4 over here. So now all we gotta do is solve for the EA here. So EA is 5.4. And then you, since this is over multiplied here, you go ahead and divide that. And then you can multiply with 8.314. And you'll get your answer in joules per moles because the Kelvin cancels off. So for that case, joules per moles, you get 1.45 times 10 to the power 5. So they ask for kilojoules, you just basically divide it by 1,000, which is 1.45 times 10 to the power 2 kilojoules per moles. Because kilojoules and joules, the difference is 1,000, right? So let's go ahead and write that down. 1,000 joules is 1 kilojoules. So 10 to the power 3 joules is 1 kilojoule. All right, so that's one problem. We'll do another one. I wanted to show you a slightly different example where we're going to be solving for your one of your K's, one of your rate constants instead. Okay, everyone follow this math here. So do we have to convert to kilojoules for the lab as well? Yeah, some people, I think in the results quiz, they actually ask you for the kilojoules. I'm not really sure, but if they do, just say, here's my answer in joules per moles. And then for the lab, you just go, because this is joules per moles, yeah, I'm going to divide it by 1,000 and get kilojoules per moles. So it depends on the results quiz. I can't remember what it asks for. But as long as you have the joules per moles calculated in your lab, you should be okay. But I think you do have to convert it kilojoules per mole. One common mistake is students forgot to use the negative sign in the slope calculation. So that one's different from this, okay? It's a separate question. You're welcome. All right, so let's do another problem here. Another 2-point form. And remember this equation here and your integrated rate law equations are on your periodic table, okay? Your constants are on a periodic table too. So basically you should have like the major stuff, you know, the itty bitty equation like first order, half-life. Those won't be on there because they're really short ones. The big ones are going to be on there, okay? First order reaction has rate, constant of 1.35 times 10 to the power 2 per second at 25 degrees Celsius. What is the magnitude of K2 at 95 degrees Celsius if activation energy is 55.5 kilojoules per moles? So now you see a problem where they actually give you all the wrong units. Okay, so I'm going to go ahead and write the equation out first. It's ln K2 over K1, and then EA over R, 1 over T1 minus 1 over T2. All right, so remember, the unit for this guy is 8.314 joules per moles Kelvin. So you want to make sure your activation energy is in joules per moles and your temperature is in Kelvin. Okay, so when you're doing your test questions or quiz questions, make sure you write this down and you're like, okay, now I know what units I need to use if I can't remember. Convert that over to joules per moles, convert that over to Kelvin, okay? So they're asking for magnitude of K2, so you're looking for this guy now. So earlier the question was asking for this. So you see how they can ask for any one of them. They could ask for a temperature, activation energy, or one of the rate constants. Whichever it is, you just basically use algebra to solve for it, okay? So let's go ahead and plug all the values in, but we do need to convert these values over to Kelvin, okay? So 25, I'm gonna go ahead and label them. So this is K1 at T1, which 25 degrees is really 298 Kelvin, so I'm gonna go ahead and write 298 right here so I don't forget. And then K2 we're looking for, what's T2? It's 95 degrees, but you need to turn it into Kelvin, so I'm going to go ahead and write it down. It's 368. Okay, so, and then this one here is in kilojoules per mole, so I just have to multiply by 1,000. So I can just write, well, this one really EA is 55.5 times 1,000. And that's in joules per moles. Okay, so it's not that much conversion really, but you have to remember to do that. Okay, so let's go ahead and put it in. Ln, we don't know what K2 is. We're looking for that. We know K1. What's K1? 1.35 times 10 to the power 2 per seconds. All right, that goes there. And then let's go ahead and put my EA in. So I'm just going to do 55.5 times 1,000 because I know the conversion 1,000 times. Joules per moles. And then R, 8.314 joules per moles Kelvin. And then you do your temperature. 1 over, what's your T1? 298. And it's in Kelvin minus 1 over 368 Kelvin. Okay, so So now leave this part alone. K2 over 1.35 times 10 to the power 2. Okay, you gotta solve this part here. So try putting this in your calculator. I wanna see what you guys come up with. Can you solve it, okay? So you get something like 4.26105, blah, 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 really long number. Around 4.26, like that number right there, okay? It's pretty long, but around 4.26. Yes, perfect, 2611, yeah, that works. But what I do is I keep that number in here. I don't round it, I keep that in my calculator. So that way I can continue with my math on here, okay? So to do that, and then you take, how do you get rid of the ln here? What do? We take e on both sides, okay? So that goes away. So now we know that K2 over 1.35 times 10 to the power 2, that equals to e to the power negative, I mean not negative, e to the power 4.26. So that number is right there. I'm going to take the e of it. So hopefully you get the same answer, about 70.89, 70.9-ish. So I'm going to go ahead and write 70.9. Okay, so K2 will literally be that number times that number now, okay? It's like 9,000 something, so 9.57 times 10 to the power 3 per second. Okay, so hopefully we are pretty comfortable. It's gonna take some practice, okay? Especially if you haven't taken a math class in a long time, you don't remember any of this math. And plus, we got formulas and math and trying to convert units and plugging it into a formula. So you want to make sure you do practice till you get comfortable with it. You don't want to, have a lot of anxiety going into your test. Just make sure you know if you can do your practice test. So I would go ahead and take that practice test. You get to take it twice, I think, and kind of see where your weak spots are. If you have like a certain area that you are not getting, and then go over those questions and then redo it to make sure you can do a good job. Definitely ask me or maybe get tutoring help or do a discussion, but I will be working through basically a practice exam with you guys. And hopefully that, when you have questions, make sure you ask them, okay? So don't like panic too much. All right, so let's keep going to the last part. Now the last part is like a little bit different, a lot of mechanism stuff. So you probably see some mechanism question and you're like, I never heard of this. This looks crazy, but we're gonna talk about it. So let's move on to the next part. We're done with the Arrhenius equation stuff. What we're going to do is we are going to talk about reaction mechanisms. So we are going to, so there are some slides on there that talks about like the collisions and collision factor and orientation factor and stuff like that. Like basically this slide here is saying, oh, if you wanted to react the green and green, the green and green has to match. Like, this is like the number of collisions and orientation is important here. And then they say that over here, that's a formula. But I'm not gonna make you calculate that A here. Basically there's orientation and collision. We already talked about that. That's how many times they attempt the collision to do the reaction. And then this is how many of them passes through. That's the exponential factor right there. Okay. All right. So we want to talk about reaction mechanism. So a lot of times when you do a reaction, you see the reactants and then you see the products, but it doesn't actually happen in one step. It takes multiple steps to get there. Okay, so the multiple steps to get there are basically simplified reactions where first you do this step and then the next step you do this, but we don't talk about it because it happens during the reaction. All we see is the reactant and product. But a lot of people do studies to see, you know, how does it actually get from reactants to products? Like what steps does it actually take? Does it turn a certain way? Does this molecule react with that one? Are there anything in the middle that we're not seeing? Those are called intermediates. And then are there any catalysts that are in their reaction? So we will be talking about intermediates and catalysts. Okay, so basically, when you write an overall reaction, so this is slide number 40 here, okay? So they're saying, here's an overall reaction. I have hydrogen gas, ICl gas, and then you make 2HCl gas and I2 gas. That's the reactants, that's the products, okay? Now, they're saying to actually do this experiment, you actually had to go to 2 steps. The mechanism is first you take hydrogen gas plus one of the ICl to make one HCl and then make HI. And you're like, whoa, HI is not even on here. Because once you make this HI here, you make one of your products, but you need another HI. You make HCl, you need another HCl. So you have this HI here. This HI is then consumed in the following step. And then take that HI plus the second ICl, and then you will get an HCl and I2. So essentially, this HI was made somewhere during the mechanism, but then it was consumed also somewhere during the mechanism, which overall you didn't see it. It was made somewhere in the middle. You did not physically put it into the flask, okay? You don't physically put it in. If you physically put it in, it's a reactant, but you didn't put HI in. It just automatically made it, and then it disappeared before the reaction was over. So that's what you call a reaction intermediate here. Okay, now these mechanism steps here, we call them elementary steps. Okay, they can't be any simpler. They're the simplest step, they're elementary steps. So you got to remember, mechanism steps are elementary step. That means you can't simplify it further. All right, so let's take a look at that. So we kind of sort of define what a reaction intermediate is. This is on slide number 41. So over here, they're saying, see here, from step 1, you didn't put HI in, but you made it, and then you used it up. So you will be required to identify intermediates in your reactants, in your mechanisms, okay? How do you tell which one's a reactant, which one's a product? Well, the reactant is something you put in. The product is something that it results in. But an intermediate is something that you didn't put in, it got made halfway through the steps, and then it got used up after that. It has to be made and then it has to be used up. You got 42.6. Yeah, you might have typed something in wrong. You want to try that again, Dylan, for the previous question there. It's because it's 10 times off. It's probably just when you're putting something in, maybe your decimal was off. Okay, so just remember the HI here is an intermediate, so we know how to identify that, okay? Now, what's interesting about mechanisms is, you know how before this I was telling you, you know, if you wanted to do the rate law for a reaction, you have to do an experiment. It's not completely true. Okay, yes, you do have to do the experiment. It has to be determined by that, unless you know the reaction mechanism. If you know the reaction mechanism, you can actually write the rate law based on the reaction mechanism, which is what we're going to be doing now, okay? So let's take a look at rate laws for elementary steps. So why do we say that? Basically, if they're elementary steps, all you do is you want to write you can write the rate for every elementary step. It's basically rate equals to K, whatever the reactant in the elementary step is. Okay, so if it's K, if it's just A for the reactant, it's just K, rate equals K times A. And then if it's there's 2 A's in there, well, rate equals to Ka times A, so it's A squared. So A would be second order here. Okay, so basically you would write it like that. And then if you have AB, rate equals to K times A times B. A and B are both first order. So you can tell, like, if there's one molecule, it's first order. If there's 2, you'll have a second order total, because overall order is basically you add the orders of each reactant up. Okay, each one is 1. So each time you write A, that's 1 order. There's another A first order. So A here is second order. So this is second order reaction. A is first order, B is first order. So you have 2 of them. So you have second order overall. But each of these reactions are first order. Okay, so if you have the mechanism, you can write the rate law. But if you don't have the mechanism, you have to do the experiment, basically. Okay, so here's basically our mechanism for these steps. Okay, we just looked at this experiment, this reaction a little bit ago. So let me show you. So over here, you have H2, ICl, HCl, HI. So remember we said if you wanted to write the rate law, all you do is look at the reactants of your mechanism steps, which means is rate equals to H2 times ICl. KH2 times ICl. You literally just write down what's in the reactant side, okay? The second one, rate is K2, this is step 2, HI times ICl. That's it, okay? So basically, if you know the mechanism, you can just write the rates for every step like that. Now that we know how to write the rate for every step, how does that help us find the rate for the overall? Because you can't write it for the overall. You can only write the rates like that for mechanism steps. So we have to figure out how to use the mechanism steps here to determine the overall rate law, okay? Because on our experiments, we did it for the overall by doing a bunch of different reaction mixtures. But over here, you can only write it for each step. So let's say you were doing an experiment, maybe like, you want to make a love potion like you were in Harry Potter. You guys remember that one, that part? Okay, so obviously they don't give us like the recipe, but let's just make it up. Maybe the recipe had 2 steps, okay? To make the love potion, you needed 2 steps. Now the first step, it took about a week, 7 days. You gotta be really patient. It has to brew and simmer or whatever it is. You gotta stir it for 7 whole days. Okay, and then there's a second step. The second step takes 10 minutes. So once you make your love potion, you're gonna tell your friends about it and they're like, well, how long did it take you to make it? Well, it takes about 7 days, right? Because you only mention, because the second step is so small, like it's so fast compared to the first step that takes up so much time. Your overall time to make it basically is dependent on the slowest step. Okay, so we are going to use the same analogy here. So the rate of the overall reaction is equal to the rate of the slowest step, which is the slow step in your mechanism. So let's say this is fast and that's slow. Well, then you would have to say the rate is this guy. The rate for overall is this line right here. If the first step was slow, then you say, well, the overall reactions rate is going to be the same as the first one. So you really need to be able to tell which one is a fast and slow step. Lucky for you, they always label it. They'll label step 1 fast, step 2 slow. They'll label it for you. So you'll be able to tell which one is a slow step, okay? Now, if you know which one is a slow step, then you can write the equations out. So let me show you again what we were talking about. So if you have A, you write like this. So you got like, if you get like triple A, then that's A to the 3rd order. See that? And then you have ABC, each one of them is first order. So basically you literally write whatever's in the reactant side. Okay, so here's what we're gonna do. It just says rate determine. So the slow step is called the rate determining step. Okay, the rate determining step is the slow step of your mechanism. And it is the same as your overall rate law because we say your reaction rate is basically held up by the slowest step. So you can just ignore the fast ones because it's so fast. You just work on the slow step and call that the reaction rate law for the overall. So I'll show you an example over here. So in the picture wise here, so when they were doing an experiment in lab, like if you did NO2 plus CO and to get NO and CO2 in lab here, you do a bunch of experiments like 4 reaction mixtures and then you find your orders that way. They find that the rate law was KNO2 squared and CO was 0 order basically. So they didn't write it. Okay, so one was 0 order and one was 2nd order. That was your experiment. But if you didn't have the experiment, if you didn't do the experiment, you wouldn't know this part. And what if you knew the mechanism? So if you knew the mechanism, this is step 1, that's step 2. And then they'll tell you the first step is a slow step. The second step is a fast step. So the rate of the overall, which is what they observed here, is the same as the rate of the slow step. Okay, so basically you just want to say, if I see the slow step, that's the rate for my overall. But you gotta be able to tell who's slow and fast, which is why they will label it for you. Okay, so the first step is a slow step, so it's called the rate determining step here. So when you take a look at the picture here, remember we talked about activation energy? The higher the activation energy, the slower it will be, right? Because less of them can hop over the big hump. Remember we said, like, if people had to jump like 10 feet high to get an A in this class, nobody will get an A. Well, maybe some of you will, but and then if the second step here is a lot faster. Why? Because the activation energy is lower. Okay, so lower activation energy will give you a faster step. High activation energy will be your slower steps. And then remember you have your little, over here, the hump here, where the top up here is the activated complex, where it's the awkward position where they're trying to twist. So that's step 1 and then step 2. Okay, now this arrow here tells you delta H of the reaction. Is this endo or exothermic? Can you guys tell? What is this? Overall reactants, go to products. These are the individual steps here. So every step has its own activation energy. But this blue arrow going down here is exothermic. Very good. Okay, and it will be a negative sign. All right, so let's go ahead and start practicing these. And after we do reaction intermediates, we want to talk about catalysts as well. Let's do an example reaction intermediate first, and then we'll talk about catalyst, okay? So I'm going to go ahead and write the question out for you. All right, so here's my steps. Step 1, A plus B2 goes to AB plus B. This is a slow step. So here's what's interesting. Right now we are learning, here's the mechanism, write the rate law based on the mechanism. We will also try to do examples where we have, here's the rate law. Can you see which mechanism matches it? I gotta, we'll do one example like that. Okay, so it's kind of like a, from the mechanism you can get the rate law. From the rate law you can identify which mechanism matches it too. Here's step 1. That's step 1. Step 2, A plus B goes to AB. This is a fast step. Now, the question here wants you to do a few things. So determine the overall reaction. So that means I write reactants equals the product on the overall, okay? Determine the rate determining step. The rate law. And identify all intermediates. Okay, so the obvious one to me is the rate determining step. Which one is the rate determining step? The rate determining step is the slow step. Right? So which one is the slow step here? Basically the first one, right? So let's go ahead and say, okay, I'm going to go ahead and just write RDS, rate determining step, because too lazy to write a bunch of words. Step 1. Why? Because it is a slow step. So that means the rate law for the overall, they meant for the overall reaction, okay, is the same as the rate for the rate determining step. Agree? So the rate law overall is the same as the rate law for step 1. Which the rate for step 1, how do you write it? Rate for step 1 is, remember we look at the reactants, right? So it will be K, step 1. You don't have to write it. I mean, I just write 1, but it just basically there's this has a rate, that has a rate, because this is slow, that's fast, and each one is a little bit different, but it's a constant. It's just a number basically. You can label it whatever you want. A, and then B2. That's it. That's the rate. Okay, that's the rate law. Now, and it says the next thing is write the overall reaction. What's the overall reaction? Overall reaction means what are the reactants, what are products, and overall reactions, the intermediates are not in there because the intermediates get canceled away, right? Intermediates get canceled away. So to write the overall reaction, we probably need to identify the intermediates first because intermediates will be canceled off and not really expressed in the overall. So let's see. A plus B2 makes AB and B. And then A plus a B. You see how the B was made here? And then the B was used up here. Okay, so it looks like B is my intermediate here. Okay, and then you get AB. So I put in 2 A's and I put in a B2. Those are my reactants. I did not put in B. B is an intermediate. And then I got 2 ABs as my product overall. Are we seeing this? So the overall reaction, so because B is my intermediate, we're going to see my overall to be, so 2 A's, right? 2A plus B2, and then I make 2AB. Because we don't put the B in. It got canceled out. If you wrote the B, literally there would be a B here, and there will be a B here. See that? Then you'll be like, oh, well, that cancels off. So you can do that too, just that's your intermediate, but it really doesn't work that way. So you never write the intermediate in there. Okay, so always identify the intermediates and then say, well, intermediate, you don't put it in, so you don't write it down in there. All right, so let's take a look at the next thing. We want to talk about catalyst. So you guys heard about catalyst. Catalyst makes the reaction go what? Go faster, right? And they always tell you they don't take part in a reaction, but they just make things go faster. And the truth is, it sort of takes part in a reaction, but not really. What it actually does, it affects the rate of a reaction without being consumed. But technically, it does get consumed at some point, but then it pops back up. It gets remade. It's really interesting. Okay, so catalysts actually work by lowering activation energy because they introduce alternative mechanisms, like extra steps or different steps that have lower activation energy, so it goes faster. So how does a catalyst speed up a reaction? It gives you alternative mechanisms with lower activation energy, so therefore it will be faster. Now, it doesn't get consumed, but technically it's consumed in one step. Early on, you do have to put it in because it's a catalyst. You put it in there in the beginning, it's used up somewhere in the middle, but then by the end of the reaction, it's already popped back up. It got remade again. So it looks like it's not being consumed, but really it was taking part in a reaction, but then it pops back up as if it was untouched. Okay, so here's mechanism without a catalyst. It's really slow reaction, O3 plus O, get 2O2. And then they say, if you introduce a catalyst, you have a fast and slow step instead of a very slow. So you basically sped things up. And then you have, let's see, Cl plus O3. So a Cl plus O3 gets O2 and ClO. And then, so you put in Cl, you put in O3, okay? And you make oxygen, O2 and ClO. And then on the second step, you use the ClO. So that tells me ClO is my intermediate here because you made it and then you used it, okay? And then ClO plus O, so you had to put an O in because you didn't make an O here, so you put the O in here, and then you make another O2 and Cl. So you had to put in Cl, O3, and O. And then you see how Cl is still at the end there? It popped back up. So Cl here is your catalyst. It was there in the beginning, but you put it in. Somewhere you have to put it in like as if it was a reactant, but then at the end it's still there. So you technically don't have to write it in your equation, but it's there. You physically put the Cl in, right? So, but it got used up, but it reappeared again. So that's how you find a catalyst, something where you have to physically put in, then it gets used up, but then it reappears at the end in the overall product side, okay? And then CLO is the intermediate here because you made it and then you used it. All right, so catalyst and the chemical reaction. No, it's the same thing, the catalyst here, but our catalysts are simpler here because it's a single molecule. You guys in the bio, like it's gonna be a bigger molecule and the mechanisms will be different. But at the same time, catalyst is the same idea. They actually talk, well, this is more like materials chemistry versus bio, but it does the same thing. It speeds up the reaction and it says it doesn't take part in it. But you do know it essentially does gets used for something, and there's a reason why it speeds things up because it changes the mechanism. Okay, they make it a lot faster by doing a different pathway. And then they'll show you, so like over here, types of catalysts, there's ones that are in different phase and the same phase. So this, we're talking more about like, I guess materials chemistry here, more like than biochemistry. Anyway, it is technically the same, but obviously they're very different molecules. So right now we're talking like for making chemicals, like making O3 and oxygen go to O here go to O2, okay? So we got the catalyst, we got the intermediate. So the reactants are O3 and O, and then my products are just O2, 2 molecules. So my overall reaction, if I had to write it, I would write it as overall would be basically this guy, O3 plus O, and then I get 2O2 right here. Because you don't have to write the intermediate or the catalyst. Okay, but at least you put the catalyst in, so you know the catalyst was there in a reaction. All right, so now that we know what the catalyst definition is, I want to give you a question where, I'll show you a slide here. See how this catalyzed, one slow step, big activation energy, you use a catalyst, little fast steps, but 2 steps, but lower activation energy, so they're faster. Okay, so that's what the function of a catalyst is. Sometimes they'll ask you, here's a chart, you know, when you put a catalyst in, what are you lowering? Well, you can say, well, the lowering is activation energy. You actually essentially do not change the delta H of the reaction. See how this delta H here? Yeah, it's exothermic, but the reactants and the product stays the same. The only thing that sped it up is not exoendothermic change here. It's actually the change of the activation energy size, okay? All right, so let's go ahead and try to do a problem here where I want you to identify the intermediates, the catalyst for me, and then we'll write the overall reaction. And then I want to show you how we can write some reaction mechanisms where you have to do substitution, okay? Now, if we don't get to the, well, I guess we'll do as much as we can. I will pick the rest up on Monday if we don't finish the last one. Let's do this real quick. It's on step 1, CH3, CH2Br plus AlBr3 goes to AlBr4 plus CH3, CH2 positive. That's step 1. Step 2, CH3, CH2 positive plus C6H6 goes to C6H6, CH2, CH3 plus. This is one thing, it's stuck together. I don't know why I had this big gap there. Step 3, C6H6, CH2, CH3 plus AlBr4 negative goes to AlBr3 plus HBr plus C6H5 CH2 CH3. Okay, so we want to find intermediates and catalysts and overall reaction. That means, right, the reactants go into products. All right. So let's take a look here once you guys are done writing it. So remember, how do you find intermediates? You did not put it in. You don't physically put it in, but it gets made and it gets used up in the mechanism steps, okay? So take a look at it and tell me if you see anything that got made, you didn't put it in. It got made, but then it got used up somewhere in the next steps. All right, we see the first one, AlBr4, great. Okay, so the first intermediate that we found, AlBr4 negative. Because why? Because made in this step, and then it was used in this step. Okay. All right, and then we found another one. Someone said CH3, CH2. Okay, let's see. CH3, CH2 plus, made in step 1, used up in step 2. Very good. Okay, so CH3, CH2 plus. And then we have another one. We said C6, H6, CH2, CH3. So this is a big giant guy. Yeah. See how it was made in step 2? And then it was used up in step 3. So that's another intermediate. Very good. Is there any other intermediates that you guys see? No. That's it, right? All right, but that's a lot. All right, so let's take a look at catalyst. Do you see a catalyst? Now, how do you define a catalyst? You have to physically put it in, okay? It somehow gets used up, but then it pops back out somewhere in the mechanism. So it's as if it was there in the beginning and was there in the end. Do you see any molecule or anything? Sometimes there's no catalyst. Just see if you find one. Very good, AlBr3. Perfect. So let's take a look. Does it fit? Why do we say that? So AlBr3, I'm gonna put a square on it. You physically put it in. It was used up because obviously you used it. You made this guy, and then that guy got used up, and then oh look, it popped back up in the end. So you see, as if you put it in there, and at the end of the reaction, it was still there, like as if nothing happened to it. But we know it took part in the mechanism somewhere. All right, so you have to physically put it in, and it has to appear back up at the end. So C6H6 here, you did put it in, but did it appear back up in the end? There's really no C6H6 somewhere here. So if that's the case, this guy is just a reactant because you don't make it back again in the end. And then you see how this guy here, you put this in here. Did you make it again in the end? You didn't. So AlBr3, you don't have to write it in there because it's in there beginning and the end, but because you do actually technically put the catalyst, and if you wrote it, you would be able to see what's the catalyst. You physically put that in there. But usually you don't have to include the catalyst in there. I'll write it in, and then we can box it on and say that was the catalyst. But anyway, so here's the catalyst. The intermediates don't ever show up on the overall at all. But you did technically put the catalyst in, right? So you were like, well, it technically was put in, but because we know it's a catalyst, it really didn't. It's in the beginning and the end. So I'll write it with. So you basically put CH3, CH2, Br. That's my reactant. And then you did put the AlBr3 in, but we know that's a catalyst because it does show back up again. And then you also put in C6H6. I circled the stuff, the intermediate, so I don't have to write it. and then you have AlBr3 made again. So you see how this was that, and that's why this is a catalyst. You technically don't even have to write it in there. Okay, and then plus HBr product plus C6H5CH2CH3. Right? So hopefully we all are understanding how we can identify catalysts and intermediates. Okay, so you just have to remember the definition, and then they'll give you a bunch of different options, and you have to be able to pick out, you know, how can you tell which one's an intermediate and which one isn't. So it's really important because intermediates, because they don't appear on your reaction in the overall, you can never write an intermediate in your rate law. You don't want to have an intermediate in your rate law expression because it doesn't, they're like, well, it's not even in your overall reaction. How can you say, but at least you put the catalyst in. But like with the rate law, if you have an intermediate, it's, you don't even put it in. How can you write a rate? They say you don't want to write a rate law with something that's not even in the overall. So intermediates, you don't get to write it if in your rate laws. Okay, so I want to show you an example where what would you do if you found an intermediate in your rate law? How would you take care of it? Okay, so that's the next part that we're going to do. I'm going to go ahead and do space. Yeah, let's go ahead and switch over to the next page. All right, so here's my next part where I'm going to give you a mechanism steps, and we're going to write the rate law. But if you find an intermediate in the rate law, we have to substitute it out. Okay, and then we probably won't have time to do the other version. Actually, I can probably skip the others and go back, and we'll do more when we come back on Monday. Actually, I might just make your class a little longer. Yeah, we'll just push it till the end. We'll just stay a little bit later. You guys okay with that? If you wanna, if you gotta go, you can just go. But most of you are signed up for hopefully the lab or whatever. If you don't have a class right at 11, we will stay a few minutes extra. So here's my overall. And then we got mechanism step 1. And 202, this is my fast step. Step 2, H2 and 202. Step 3, N2O plus H2 and 2H2O. All right, so this is basically, see how they draw other steps and told you which one is fast and slow? Okay, so remember, we gotta pick our intermediates and catalysts. So we know that if you see an intermediate in your rate law, you wanna substitute it out. So you see any intermediates here? Let's go ahead and write intermediates out if you see any. And let's look for catalysts if we see any. And then find our rate determining step. Obviously that's step 2, right? Because that's a slow step. So what can we go ahead and write that? Step 2. So take your time. Tell me which one is your intermediate. Do you see an intermediate? N2O2, let's take a look. Yep, it was made, it was used. Okay, N2O2. You see another intermediate in there anywhere? Any more? Oh yeah, you can keep the catalyst in the overall. It's not wrong. You definitely don't keep it in for intermediate. Okay, you can write the catalyst in the overall, but it technically gets canceled out anyway. But you did, since you did physically put it in, you can write it in because technically it was a catalyst. You did put it in, so you can write it in the equation for the catalyst. Don't write it for the intermediates. Okay. Next one says N2O. N2O, yes, it was made and then it was used. H2 in this case here, it was put in and it was put in. So you technically put in 2H2. That's why the reactant says 2H2 there. So H2 would be a reactant right there. Okay? So we got this reactant, that one, this reactant, and that's my product. And you got 2H2O here, that's why there's 2 over there. So it kind of matches that once you cross off your intermediates. So because they're all there, that means there's no catalyst, right? I mean, I don't see any catalyst. None. Okay, so just remember, if you didn't use, intermediates don't get put in. They made it somewhere and then they used it up. But then if you actually physically have to put it in, because you put it in over here and put it in over here, because you didn't make it on these steps here. Okay, and those are just gonna be your reactants. All right, now remember catalyst is you physically put it in, got used up somewhere, and then pops back up somewhere in the end. Okay, so those are how you identify it. So since we know that step 2 is a slow step, we do write the rate law for step 2 as the rate of overall. So the rate for step 2 would be rate for overall, which is what we're looking for, the rate law. So I'm going to go ahead and write the rate law, which is rate equals to K of step 2 times H2. Just basically look at the reactants times N2O2. Now remember we said we don't write intermediates in their overall reaction, so then you don't want it to appear in your rate law as well. So in this case here, this here is bad. This is not good because this is an intermediate. You really don't want it in there. Okay, so now we got to find out a way to turn that frown upside down. Does the catalyst have to be to start from? No, the catalyst does not have to start from the first step. You can, the catalyst can be in there from the middle steps too, as long as you physically put it in. Okay, so if you take a look at the previous one, I think it wasn't in the first step. Oh, it was in the first step. But no, you don't have to always have it in the first step. Sometimes it's in the middle that you put it in. It doesn't matter. As long as you put it in, got used up, and then it appeared back again. Okay, and not always in the first step. It doesn't always have to, be in first or second step, whatever. As long as you put it in somewhere and then it comes back up. All right, so back to this one, intermediate here. So what we want to do is when you see an intermediate on a slow step, you have to look at the step before that. And the step before here is a fast equilibrium. So this reversible arrow here, remember we talked about equilibrium, how like when we talk about vapor pressure, how if you have a rate of vaporization and a rate of condensation, when it reaches equilibrium, that means the rate of forward, which is evaporation, it equals to the rate of condensation. So it looks like it's not changing. It reached an equilibrium, dynamic equilibrium. That's what this symbolizes here. So when you have a double arrow here, and if it says it's fast, that means after this fast step, it has reached equilibrium, and then it takes the second step. So when you take a look at the first step here, you can say because the first step has dynamic equilibrium, so if this is a stat for line 2, take a look at line 1. At line before it. So line before number 2, which is 1, okay? Line 1. So line 1 is a fast step at dynamic equilibrium, where rate forward of the reaction equals to the rate of the reverse direction. That's what the dynamic equilibrium meant, okay? So just kind of show you up here, this is what that means. So I'll zoom out a little bit. You guys can still see it, right? Oh. Well, it's way up here. You have it in your book. Just go look at line 1. So rate forward and rate reverse. So how do you write the rate forward for line 1? Let's go ahead and write that. Rate forward for line 1 is this forward, right? So it's rate equals to K1, and then because there's two NO, you say, well, there's two of them, so it's square. Okay? How do you write the rate of the reverse for line 1? So that means if it's reverse, it's starting from here to go to there. So that means this is what I start with. So it'll be rate equals to K times N2O2. Okay, so because it's going backwards, I want to make sure I distinguish it from the other one and just write -1, means the opposite way. Okay, it's just a constant, it doesn't really matter, it's really just a number. Okay, N2O2. Now we did say, because it's dynamic equilibrium, rate forward equals rate reverse, these two are equal to each other. So you can essentially write K1 NO2 square, not 2. Let me erase that out. To the power 2 equals to K reverse. This is really the reverse of direction, N2O2. Okay? So what this means here is you can now find an equation where the intermediate is described using something else that wasn't intermediate, those terms. So N2O2 can be rearranged as actually K1 NO to the power 2 divided by K minus 1. Agreed? So you can literally write, well, basically it's just K1 over K minus 1 times NO squared. So this term here equals to that term. So I can replace that intermediate with this big term here. And this here is not an intermediate, it's NO, it's a reactant. So that works out for me. So you just basically find a substitution by looking at the line before that, write the rate forward equals to rate reverse, put them equal to each other, find an algebraic substitution for it, and then put it up back in the spot you don't want it. So the rate now for the overall is K2 times H2, and then the N2O2 becomes this big term here, okay? I'm gonna write it over here. So times K1 over K minus 1 times NO to the power of 2. So what I like to do is to make all the K's come together. It's a constant times a constant becomes a different constant. So I'm just gonna go and write, this is K overall rate, and I'm gonna note on the side here, K overall is really K2 times K1 divided by K minus 1. And then that's K overall right here, and then you have H2 times NO squared. That means here's your rate. Your rate is H2 to the power of 1 first order, NO to the power of 2 second order. Okay? So that's how you would find your overall rate. So now it's a smiley face. Everyone good? All right. Let's do one more of the same kind, and then I want to do the opposite one, okay? All right, so I'm gonna go ahead and write the new question. Hopefully you guys are done writing with this. All right, now the next one I want to do is this. O3, this is step 1, reversible step. O2 plus O, this is fast. And then number 2, O3 plus O. 202, this is my slow step. So find overall rate law. Okay, so now what we want to do is, well, the slow step is the rate determining step. RDS is step 2. Do we see any intermediates? I like to write it out because if you see an intermediates, you gotta make sure you know. Okay, so help me point out the intermediates or catalysts if you see any. Intermediates, anybody? O? Okay, let's see. O, you made it. O, you use it. Very good. So that's our intermediate. I'll write it down. O. Well, since it's just 2 steps, there's really no more intermediates because O2 didn't get used up. O2 is a product. So my overall reaction, so there's no catalyst, doesn't look like it. So my overall reaction looks like this. O3, my reactants, O3, there's two of them, goes to 3O2. Because there's two here and there's one, so it's three total. That's my overall, okay? So let's go ahead and say, write the rate law now. So we gotta write the rate law for step 2. So rate for step 2 is K for step 2 times O3 to the power 1 times O. Agree? And because that was an intermediate, you're like, oh, sad face. Intermediate. Now I have to do algebra. Okay? So how do we do that? Remember, we take a look at the line before it. So take a look at line 1, and then we write rate forward equals to rate reverse. Okay? So rate forward equals to rate reverse. We'll have to write that out. So I'm going to go ahead and write down the rate forward first. Okay? So rate forward is what? K step 1 times O3. Agree? And then if we want to write the rate reverse, basically these are your starting points here. Would be K opposite side O2 times O. All right, and then we put, can you explain the 3O2 again? Oh, the overall here, see how these are my intermediates so they don't appear on my overall. And then you have two oxygen, O3, ozone here. And then you have two oxygen in a product here, and you have another oxygen in your product. So 2 plus 1 equals 3. So I just wrote overall 3 right there. Okay? You're welcome. So we're back here. So now I want to, this equals to that, okay? So that means K1 times O3 equals to K negative 1, which is just the opposite side. It really isn't a negative number. It's just the opposite direction. O2, O. And then what am I trying to replace? I'm trying to replace the O, the intermediate. So this guy has to be established as an expression. So I'm going to write O on the one side. And then all the other stuff goes on the other side. So it's K1, O3, and then you want to divide by K opposite 1, O2. That's what it basically says. Okay, so if we want to write it again a little bit nicer, so that is K1 over K minus 1, O3 to the power 1, O2 to the power of negative 1. Because it was on the bottom, I just brought it back up. You take this term here. The reason why it's to the power negative 1 because it's a product, it's on the bottom. So now we take this and put it over here. Okay, so now the rate equals to K2 O3 times K1 over K minus 1 O3 O2 negative 1. All right, so I'm gonna go ahead and combine the K's so I can get a K overall because I don't want to write a bunch. So you can actually do this. You can write K2, K1, K minus 1 like that. Or you can just say K overall. A lot of times you just hit K overall. And then O3, see there's two of them. So I'll just put a square and then O2 to the power minus 1. Again, so basically K overall is K2 times K1 over K minus 1. So we'll put that in there. So now that is like K overall. O3 to the power 2, O2 to the power negative 1. Okay, so that's one example. Now, I had another one, but let's do the opposite one first because like, you know, you've seen one, you can repeat it, basically just always substitute it. Okay, I will do the opposite one now, where now I'm going to give you a rate law and ask you which mechanism will fit it, okay? What does K2 represent? K2 was just a K rate constant for step 2. I just wrote it there from earlier. Okay, so K2 was basically, whatever step it is, you just write the K for that step. It's just so you know which K you're referring to, because they're all different numbers, okay? All right, so I'm gonna go ahead and switch over. Oh yeah, gotta do a quick poll. I'm gonna do a poll here. Poll. Here's one. What's your favorite cuisine and what's a good local restaurant or recipe for it? Pick your cuisine and type out the restaurant for it because we want to know. You got to share your secrets. Pizza. What's the best pizza around? So take a look at that and I'm going to go ahead and write the question out, okay? This is something that's, very possible. Like these mechanism questions will show up on your test and you'll see them. Cl2 plus H2S comes to S plus 2H plus 2Cl negative. So, oh yeah, I gotta read out the options. So what's your favorite food, right? So pizza, sushi, wings, Chinese takeout, Italian, Asian. So there's a lot of Asians, Thai, Vietnamese, etc. Mediterranean and seafood, Mexican. Who doesn't like tacos? Something else not listed here. All right, Cuban food, La Teresita. Where is that one? Lemongrass in St. Pete, Pizza Hut, Thai Basil, Sushi Robloto in downtown St. Pete. Mexican place, we forgot the name in Pinellas Park. Oh my gosh, I'm gonna have to read your chat today because there's so many ideas here. Mexican food, Grand Hacienda, My Grandma's Kitchen, Tasty Pho. There's so many. Taco Dirty, I've heard of that. It's so funny the name Taco Dirty. Sushi Kabuki, Benito Sushi, KBBQ, Korean barbecue. Is there a good place for Korean barbecue? There are so many options. All right, for those who have to leave, you guys, make sure to catch the last part of this, okay? I will be posting the video later today. Best Chinese takeout, China Express in Tarpon. Somewhere in Tampa, Boil Spot. 9 Spices, Boil Spot, I have to remember that. 9 Spices Korean Hot Pot. That sounds yummy. Taco Dirty is so good. Red Mesa. Nam Viet. One family has the best K barbecue. There's so many options, guys. Dun River Island Cafe, Jamaican food. Wow, I love Jamaican food. That's awesome. There's a lot of options. All right, for you guys who have to leave, go ahead. That's okay. Make sure you watch the end of this, okay? Make sure you do watch because it's important. Yummy. Okay, catch back later, guys. Make sure to catch the end of it. So we're gonna continue here, and looks like food is something really important to us. We're all really hungry, so I'm gonna hurry up and finish this. End poll, share the result, pizza won. Everybody likes pizza. I've never met a person that doesn't like pizza. Stop share results. All right, so let's get back to this last question here. I don't know if anybody actually doesn't like pizza. But, I was raised in a different continent. Pizza was a rarity. We don't really eat pizza. When does the lab Zoom start? It will start at 11. I'm going to hurry. If I'm late, tell people to wait, okay? Sometimes there's only like 2 people on there anyway, so we'll be okay. I'll hurry. Okay, I'll stop talking. Which of these requirements, which of these mechanisms? Which of these mechanisms is or are consistent with the rate equation, basically the rate law given? Okay, we got 2 options. Cl2, H2S, H plus Cl. So if you notice, they'll make this look really complicated, but remember, we're not looking at products. We are only looking at the reactants, and we only identify intermediates, so it shouldn't be, it looks overwhelming, but don't get scared by it. All right, so I have this right here. We have two separate mechanisms, and we have this rate law here. So your job is basically to go through the mechanisms here and look at the steps and see what the rate law would be. So what I do is basically just write the rate law for this, write the rate law for this, and you see which one matches. Okay, so let's go ahead and try to write the rate law for this first mechanism. So our slow step is the first step, right? So that means it's right here. And do you see intermediates? We can kind of put intermediates in. Doesn't, well, there's Cl plus, looks like it. But it doesn't affect us because your intermediates are not going to appear in, like in step 2 here. You're not using step 2, you're writing the rate law for step 1. Right? So, but it was good practice. So we can say, well, the rate for the first one, the rate law here basically means it's a slow step. So it's K step 1 Cl2 times H2S. Does it match? Yeah, it matches. See that? Okay. Let's take a look at the second one, okay? Now this K here is just a K constant, so it doesn't, like, as long as it's a K here, it doesn't matter if it's K1 or K something else overall, okay? So let's take a look at this one. Is there intermediate here on the second one? I see intermediate, right? Which one is your intermediate? You have this guy. It was made and then it was used up. Okay, so that's important. We gotta know that. And then the slow step is the second step. So this is the one you have to do a little bit of substitution. Agree? So I'm going to go ahead and write the work on the bottom here for the step. So for mechanism 2, we want to write rate step 2 is a slow step, that's a slow step. K2Cl2 and then HS negative. But this is a sad phase. So we got to replace it with the step from before that, which is up here. And I'm going to write, so take a look at 1, and then we'll write rate forward equals to rate reverse. So we'll do rate forward is K1 times H2S, that's rate forward. And then rate reverse is K opposite 1 H plus and HS. Okay, and then I'm going to put these two together. K H2S equals to K H plus HS, like that. And then we'll want to basically replace this term so all the other guys go on the other side, okay? So I'll rewrite it out for you. It looks like this. Then we take this, or we can rewrite it again. So it's Ki, okay. I, and then it's H2S times H plus -1. Take this big term, we'll turn that frown upside down right here, replace it, okay? So I'm gonna rewrite on the bottom. So my rate is K2 Cl2 and then K1 K. I should have put double I here if I wanted to be consistent. It's the same thing, it doesn't matter, it's just a labeling, okay? And then H2S, H plus -1. And then I'm gonna lump all these guys together, call it K overall. And then Cl2, H2S, and H plus. Well, it doesn't even match anyway, so it doesn't matter. But we got extra practice. K overall equals to K2 times K1 over K minus 1. That's like, so we practice a lot of substitution, right? So hopefully that helps. Now you saw that this one here doesn't match because it's Cl2, H2S, and H plus -1 doesn't match the question's rate law. So only the first one matched. That means this one didn't match, this one matched that rate. So your answer is A.